Hello everyone, welcome to my channel. This is an educational channel and we're on our 481st video of covering the reciprocal system of theory from Dewey B. Larson. A lot of videos on the reciprocal system of theory. Mr. Larson was an engineer who lived in the US in the 20th century. In 1959, he proposed his two fundamental postulates about how the universe operated. And then he took his fundamental principles, fundamental postulates, and elaborated them into a theoretical universe. And then in books like the book we're looking at today, Basic Properties of Matter, Larson compares his theoretical universe with the empirical measured universe of the mainstream legacy scientists that they compiled in their scientific tables. And so we're looking at chapter 10 right now of this book that is called Electrical Resistance. Earlier chapters covered like melting point, boiling point, and a specific heat, compressibility, interatomic distance. And so now we're looking at electrical properties. We just got done with a chapter on electric current, and this is on electrical resistance. Now, if you want the rundown of the details of Larson's reciprocal system, you're going to have to go to one of my earlier videos. I did 474 videos where I explain the reciprocal system in at least some detail, enough for you to be able to follow along, I think. But you can try following along right here, and hopefully I'll be able to explain some things. The main point that you just need to really get is that the reciprocal system is a theory of everything. So it has universal application. So even though we're just talking about electrical resistance today, electrical resistance has analogs in other fields. And so the results of this study can be applied into other fields, and it can be applied generally and broadly. So we're not really just looking at this for the sake of understanding electrical resistance. We're looking at this for understanding how Larson goes about formulating a theory of everything and how it can you can use it in your own life. Because Larson does have books also not only on chemistry but on atomic physics and astrophysics and astronomy and economics and philosophy and psychology. There's some stuff on biology. There's some stuff on religion, and some of his other associates have written in further fields. So now, when we left off last time, so anyway, one of my first 474 videos on the reciprocal system will give you the once-over on the reciprocal system, and then you'll be able to follow along with these subsequent videos. Now, we're going to go back half a paragraph here. Larson is about to present this table, and it's on temperature at zero resistance. So what Larson does is he arrives at an equation for the zero resistance of atoms, and then he applies his equation to every atom, and some molecules, and then he compares the results with the scientific tables. And now what he was doing earlier is he was kind of complaining that it's pretty hard to do this particular thing with resistance because the experimental results from the legacy scientists are notoriously inaccurate, and they haven't worked out all the kinks, in particular having to do with the purity of the sample. If the resistance of a conductor is thousands and thousands of times lower than like the resistance of an insulator. And so if a sample of a conductor has even a tiny amount of an impurity, an insulator within the conductor, then it completely skews the experiment. And so you have to be very careful about making sure that you have a very pure substance if you're measuring the resistance, in particular of conductors. So, and there are other reasons too why the experimental data is kind of lacking. And so Larson was basically just saying, well, I think the agreement that I got with the scientific tables is pretty much as good as you can expect, given that the uncertainties involved in the experimental process. Okay, the existence of this amount of agreement, in spite of all the influences tending to generate discrepancies, is about as good a confirmation of the validity of the theory as a general proposition as can be expected under the existing circumstances. Furthermore, it is not unlikely that there are alternate resistance patterns that result in explainable deviations from the calculated values, and some of the larger discrepancies may be thus accounted for when an investigation of broader scope is undertaken. Okay, so Larson actually uses pretty much the same equation that he uses for determining the specific heat, one of the temperature relations. I think for the initial temperature, the T sub 1 is what he called it, I think. He uses the same equation and he plugs it in here. And in some cases, like lithium, he calculates that this is the temperature of zero resistance. Now, remembering that, we got the phenomenon of superconductivity. Superconductivity is normally only for very, very cold elements. Like if it doesn't have any heat, because heat is related to space, and the electron is a rotating unit of space. And so the relationship between space to space is not motion. The relationship of space to time is motion. The atom is made mostly out of time. And so the electron passes through matter made out of time very easily, but it does not pass through space. And so when an element is heated, it starts to lose its it starts to gain resistance very quickly. And so most of these atoms, it has a temperature of zero resistance. So kind of below this temperature, the atom is superconductive. But above this temperature, it starts to get resistance. And so for example, here with lithium, he calculates that the temperature of zero resistance would be 56 degrees Kelvin. And that is observed. It is observed to be 56 degrees Kelvin. But then here he has an equation here for sodium, and he predicts that would be 24 degrees Kelvin, and the actual observed result, again, the observed result could be wrong. It could be inaccurate as well. In fact, it's probably more likely that the theoretical value is accurate than the experimental value in this particular case, according to what he said earlier anyway. So he predicted that the temperature of zero resistance for sodium would be 24 degrees, but it's actually 30 degrees. Here with potassium, he predicts that to be 16 degrees, and the observed value is 17 degrees. But on the other hand, for example, he has, let's see here. He's actually pretty close in most situations. Gallium, he predicts this to be 16 degrees, and the observed value is 31 degrees. Other than that, he's at least, he's within a handful of degrees, usually in most of the cases. No huge, no huge discrepancies. Um, Especially given how inaccurate the results are supposed to be. Okay, let's go to back to the text. For the second defining value of the resistivity curves, so the first value, when you're putting together the curve, is the temperature of zero resistance, or I guess you would call that R sub zero. Or I think resistance is usually R. For the second defining value of the resistivity curves, we can use the temperature coefficient of resistivity, the slope of the curve, a magnitude that reflects the inherent resistivity of the conductor material. The temperature coefficient, as given in the published physical tables, is not the required value. This is merely a relative magnitude, the incremental change in resistivity relative to the resistivity at a reference temperature, usually 20 degrees Celsius, which is 293 degrees Kelvin. Plus, what is needed for present purposes is the absolute coefficient in micro-ohm centimeters per degree, or some similar unit. So, didn't quite understand that, but he's looking for the absolute coefficient of resistivity as opposed to the relative, which is what the scientific tables provide, is the relative resistivity at a reference temperature, usually 20 degrees. He's looking for an actual value that is like on a per degree basis, so that can be plugged in at any temperature value. Some studies have been made in this area, and as might be expected, it has been found that the electric one-dimensional speed, electric and one-dimensional are basically synonymous, that the electrical speed displacement is the principal determinant of the resistivity. Okay, so now in Larson's atom, he's got three numbers for his periodic table. Two-dimensional rotations. Again, Larson is the universe of motion, so everything is made out of motion, and your atom is made out of two-dimensional rotations and one-dimensional rotation. That the third, so those are A, B, and C numbers. The C number is the electric speed displacement, or the electric rotation. So he's saying it has been found that the electric speed displacement is the principal determinant of the resistivity. So this is the major factor that goes into that third number, the C number in every atom, is the major determinant for the resistivity, in the sense that it is responsible for the greatest amount of variation. However, the effective quantity is not usually the normal electric displacement of the atoms of the element involved, as this value is generally modified by the way that the atom interacts with the electrons. The conclusions that have been reached as to the nature and magnitude of these modifications are still rather tentative, and there are major uncertainties in the empirical values against which the theoretical results would normally be checked to test their validity. The results of these studies have therefore been omitted from this volume, in conformity with the general policy of restricting the present publication to those results whose validity is firmly established. The experimental difficulties that introduced uncertainties into the correlations between the theoretical and experimental values of the resistivity do not play as large a role in the relative resistance under compression. The compression results, therefore, give us a more definite and unequivocal picture. Again, however, this initial exploration of the subject, as it appears in the context of the reciprocal system of theory, will have to be confined to the regular pattern, the one followed by most of the metallic conductors. Because the movement of electrons, units of space, through matter, which is time, is the inverse of the movement of matter through space, the interregional relations applicable to the effect of pressure on resistance are the inverse of those that apply to the change in volume under pressure. Remembering again that the interregional relations have to do with moving across a sector boundary. There are really 4 sectors of Larson's universe. The 4 regions, 2 sectors, 4 regions. We got the material sector and the cosmic sector, and they're divided by the unit speed boundary. And then within the material sector, which is on the slow side of the unit speed boundary, within the material sector, we have another boundary that is related to the unit of space. Everything less than 1 unit of space is in what he calls the time region. This is because of the discrete unit postulate. You have to have a full unit of something before you have something. And so if you don't have a full unit of space, you don't have space. And so instead, you only have time. And so if 2 particles approach each other to 1 unit of space, they can't get any closer because there is no less than 1 unit of space. So instead what they do is they move apart in time, which is the equivalent of moving closer together in space, because space is the reciprocal of time. So if you move apart in space, in time, you're moving closer together in space, or the equivalent thereof. Larson refers to that as equivalent space, and he refers to the whole thing as the time region. But if you are peering into the time region from the rest of the material sector, which he calls the time-space region, somewhat confusingly, there is a lot lost in the translation of looking across that unit space boundary. First, what you see in equivalent space is really a 2-dimensional projection of a 1-dimensional motion. And secondly, what you see is reduced by the interregional ratio. And so that's what he's saying. The interregional relations applicable to the effect of pressure on resistance are the inverse of those that apply to the change in volume under pressure. We found in chapter 4 that the volume of a solid under compression conforms to the relations of P times V, volume, pressure times the square of the volume, PV squared, equals K, a constant. By reason, now this was from chapter 4, this is the pressure volume, which is an offshoot of Boyle's law, which is E equals PV, energy equals pressure times volume. But since we are in equivalent space in the time region, the volume has to be squared. And so instead we have PV squared equals a constant. I guess that would be under constant temperature, since the K energy was related to temperature. By reason of the inverse nature of the electron movement, the corresponding equation for electrical resistance is P squared R equals K. So now it's the P part, the pressure, that is squared, and resistance moves in as opposed to volume. So pressure to the second power times resistance equals K, equals a constant. As in the compressibility equation, the symbol P in this expression refers to the total effective pressure. If we give because there's an internal pressure, which has to do with the progression of the natural reference system, and then there can be an external pressure that is related to, external factors. If we give the internal component of this total designation P sub 0, as in the volume compressibility discussion, and limit the term P to the externally applied pressure, the equation becomes the quantity P plus P sub 0 to the second power times R equals K. The general situation with respect to the values of the internal pressure applicable to resistance is essentially the same as that encountered in the study of compressibility. Some elements maintain the same internal pressure throughout Bridgman's entire pressure range. Some undergo second-order transitions to higher pressure P sub 0 values, and others are subject to first-order transitions, just as in the volume relations. A second-order transition is when you change the rotations that are involved in the, again, the A and B and C rotations that are involved in the phenomena under consideration. And a first-order transition is when you change the geometrical packing of the of the array of atoms, how far they are apart, and if they are in a hexagonal close packing pattern or tetrahedral packing pattern. These things also change the geometry. So these are two transitions that the atoms can undergo that will usually subtly change, at least in terms of the first order transitions, not so much in the second order transitions, will subtly change the values of the, in this case, the resistivity. Okay, so some undergo second-order transitions to higher P sub 0 values. Others are subject to first-order transitions, just as in the volume relations. However, the internal pressure applicable to resistance is not necessarily the same as that applicable to volume. In some substances, tungsten and platinum, for example, these internal pressures actually are identical at every point in the pressure range of Bridgman's experiments. In another and larger class, the applicable values of P sub 0 are the same as in compression. But the transition from the lower to the higher pressure takes place at a different temperature. The values for nickel and iron illustrate this common pattern. The initial reduction of the volume of nickel took place on the basis of an internal pressure of 913 megakilograms per square centimeter, somewhere between an external pressure of 30 million kilograms per square centimeter, Bridgman's pressure limit on this element, and 100 mega kilograms per square centimeter, the initial point of later experiments at very high pressure. The internal pressure increased to 1,370 megakilograms per square centimeter from AZY factors. Those are basically A, B, C factors with a small variation. 481 to 481 and 1/2. In the resistance measurements, the same transition occurred, but it took place at a lower external pressure between 10 and 20 megakilograms per square centimeter. Iron has the same internal pressures in resistance as nickel, with the transition at a somewhat higher external pressure between 40 and 50. I guess that would be mega kilograms, even though the M isn't there. But in compression, the transition did not appear at all in Bridgman's pressure range and was evident only in the shockwave experiments carried out at much higher pressure. All right, let's see. Sorry, I just got lost there. Don't know where I am. Okay. Table 25 is a comparison of the internal pressures in resistance and compression for the elements included in the study. The symbol X following or preceding some of the values indicates that there is evidence of a transition to or from a different internal pressure, but the available data are not sufficient to define the alternate pressure level. Okay, so this table 25, the internal pressures in resistance and compression. Now remember, Bridgman is the original investigator in this field, and he was doing his investigations in the early 20th century, I believe. But since then, there have arrived these shockwave techniques, which are able to get to a much higher pressure level and be able to measure compressibility and what you call not thermal expansion, but I guess it is compressibility. What the volume, how much you can compress the volume, depending on the amount of pressure you're putting on it. And so we will take a look at some of the ins and outs of this table tomorrow as we move through this chapter. I think we'll probably finish the chapter tomorrow, but we will conclude today at this place. Now, just keep in mind that we may have covered a lot of ground here that you're not familiar with. But again, the main point is to recognize that we're dealing with the theory of everything. So Larson is going to use these same techniques and the same thought process when he applies this to any subject. And so we're just kind of trying to glean, some breadcrumbs of how does he go about doing this? What's the process of formulating a theory of everything and then applying it broadly? And he's applying it narrowly here to this concept of compression, or of really resistivity, and comparing it with compression. But how does this apply to other areas? And I brought up earlier this week, he was talking about the pressure and temperature relations, and these are very applicable to, what you would call alchemy. When we're talking about earth, air, fire, and water, we are talking about, solid, gas, vapor, and liquid. And so Larson has a whole process of heating up an atom and all the different stages an atom goes through when it is heated from zero absolute temperature, where there aren't any atoms really, and the atoms get formed at very, very, very low temperatures on the absolute scale. And then gradually they're heated up and they go through various transitions before they get to the melting point. And so this is, a very good tool to really understand the solid state. And this would be the earth element. And then Larson has a set of papers on the liquid state. And, if you study the liquid state, then you could really understand the water element of alchemy. So these do have broad applications, but you just have to be somewhat creative and open-minded when you look at the different areas. And when you do study Larson, and that's why we spent so much time with him, you really need to go into all the different fields that Larson wrote on and kind of see how he does it in these fields and see that he's applying his principles consistently, regardless of whether it's astronomy or chemistry or atomic physics. Whether you're talking about an atom or you're talking about a solar system, the rules are pretty much the same. They're applied slightly differently, but we're talking about a universe of motion. And, there's certain rules that are involved, but the main thing is that if you got a universe of motion, motion exists before anything else does. And so motion is always in the background. There's always this progression, the progression of the natural reference system, and it occurs at all times in all places, and it's occurring at a certain speed, and that is the source of everything. And then everything, all manifestation, comes from kind of modifications of that source. And so that is kind of the major paradigm shifter that you get. Okay, well, we will be back tomorrow to finish this chapter on electrical resistance and look into table 25, and I think there's another table here after that. And thanks for tuning in today.